Hi, this is Shreyas. So, the Maxwell-Boltzmann distribution, let's understand what that is. So, first of all, just know that the distribution is given by this expression. We'll see what that means. Uh, so, yeah, so this is how a Maxwell-Boltzmann distribution for speeds of a gas looks like. So the x-axis is speed, obviously, and the y-axis is probability density. So I'll get to what that means in a while. So why is this useful? What's the importance of this distribution? I wanted to calculate what is the probability that this specific argon particle has a speed of 200 meters per second. I wanted to calculate that. So now just think about this logically. The probability that that particle has an exact speed of 200 is actually zero, because the possible speeds are actually infinite, because you could have 200, you could have 200.00001, 200.0000001. So the probability that the speed is exactly 200 is zero. But now I ask the question, what is the probability that this particular argon particle has a speed between 199 and 201? Now this is not zero, right? This has to be some finite speed, because now my interval is of length 2, 199 to 201. So this graph would help me find that probability. So what probability density means is that I could find the probability that the particle has speed from 119 in the range 199 to 201 by by integrating, or in simple terms just finding out the area under this graph from 199 to 201. So let's say from this point to some point here, the area under that curve in that range will be the probability that the particle lies in those speeds. So that is the importance of this curve, and it's a really important curve, because if you've seen my other video about the simulation, molecular dynamics simulation, then you would know that at some point we had to initialize the velocities of the argon particles. And how would you initialize those velocities? You can't initialize them randomly, because you have to initialize them for a particular temperature, right? If you initialize them randomly, the temperature would be just, some random value. So you would pick the probability density from which you would pick the velocities as this expression. That is the importance of this expression. So now you know how this expression can be used and what's the importance. So and as I said before, this graph takes care of the fact that we have maintained some particular temperature, or rather the gas is at some particular temperature. So what would happen if I decreased or increased the temperature? So let's plot that and see. So okay, let me just write the expression for that. Yeah, so as you can see, I'll just go back to that. This probability density depends on this factor of v square and e raised to minus v square, uh, which is what I've done here. Here x corresponds to v, so x square and e raised to minus x square, and temperature is this thing right over here. Yeah, 1 upon t raised to 3 by 2 and 1 e raised to minus 1 by t. That's what I've done here. So yeah, this is what the graph would look like, which agrees with this, right? This is approximately what we have got here, right? So now, what would happen if I decrease the temperature? Um, Before actually doing that, let's predict what would happen. So when I decrease the temperature, the number of particles with a higher velocity would decrease, right? So the probability of a particle having a lower velocity would now be higher. So this entire graph would sort of shift to the left. Okay, that is what should happen. Also, uh, just when I said that the area under this curve gives the probability, keep in mind that if I take the entire area under this curve from 0 to infinity, the area would be 1 because the probability that a particle has speed from 0 to infinity is 1, right? What else could it have? What kind of particle would have a negative speed? I don't know. It doesn't. And we ignore this part because this is just a result of this graph, but actually this has no physical meaning. So yeah. So if I decrease the temperature, this entire graph would shift to the left, but to compensate for the area, let's see what happens actually. So if I increase this, it kind of flattens out and goes ahead, and if I decrease this, it comes to the left and its height increases. So why does the height increase? The height increases because the total area under this curve is 1. And to maintain that area as 1, the shifting of the graph to the left is compensated by its height increasing. So that was about the Maxwell-Boltzmann distribution for speeds of all particles of a gas. Um, so just to bring more clarity, let's try and understand an example of how this can be used. So say I have 1,000 particles of argon and I want to give each of them some speed, and I don't want to assign a random speed to them because I want to ensure that after assigning speeds to all those 1,000 particles, my temperature, my system's temperature is say 300 Kelvin. So for that, what I'll do is in this expression for probability density, I'll replace T by 300 and feed this into the computer. Now, what the computer will do is for each of the 1,000 particles, it will pick a random speed based on this probability density and assign it to the particle. So after assigning speeds to these 1,000 particles, I'll have a system whose particles are moving around, and that system's temperature will approximately be 300 Kelvin. So I've used this term a lot, picking speeds from this probability density. So what exactly does that mean? So we can understand what picking from a distribution means from the example of playing dice. We know that each face of a dice has 1 by 6 chance of rolling up, 1 by 6 probability of rolling up. So if I pass this function to a computer and say that, hey computer, roll the dice 600 times. So what the computer will do, each time the computer will look at this function and pick a face based on these values. So at the end of 600 rolls, what you'll see is the face 1 turned up 100 times, and each of the faces turned up 100 times, or rather approximately 100 times, um, because each of them had equal probabilities. We could have some kind of discrepancy, like say face 1 turned up only 95 times, but face 3 turned up 105 times, something like that, but approximately each one will be 100. But say now instead, you don't want to give the computer equal probabilities for each phase. Let's say you wanted to simulate a die which had a point instead of the sixth phase, like the area is 0. So hence the probability of 6 turning up will be 0. And say the dice had phase 1 with double the area as compared to a normal die, and its probability was 1 by 3 now. So based on this function, if you tell the computer to pick a phase 600 times randomly, then so each time the computer would look at these values and pick a phase, and at the end of 600 rolls you would see that the phase 1 has been picked approximately 200 times, but the phase 6 won't be picked at all. So that's how you bias the dice based on these probabilities. So the same way, you can pass a probability density to a computer and tell it to pick the speeds from this probability density. And that is what it means in this probability density. It means that particles in this range have a higher probability of turning up. That is, when the computer is assigning the speed to those 1,000 particles, um, the probability of assigning a speed in between this range is actually more. And so more particles with these speeds will turn up within those 1,000 particles. That is precisely what it means to pick a speed from a probability density. So, so now I assume we've achieved some clarity on how we would pick speeds out of this Maxwell-Boltzmann distribution. But this distribution is only for speeds. Let's say, let's continue on the example of our 1,000 particles. Let's say instead of assigning speeds only, you actually wanted to assign component by component velocities. So each particle would have a velocity in the x, y, and z direction. So how would you do that? You can't do that based on this probability density because this is invalid for assigning component-wise velocities. For that, we have a different probability density. So this function right here gives the density for velocities in one direction. So you can use this to assign component-wise velocities. So this curve looks like a bell and it's symmetric about the y-axis, which makes sense because a particle would have equal probability of having -1 velocity in one direction as it would have of having around +1 velocity in one direction. And this would ensure that the gas as a whole doesn't have any velocity. Like even though the particles keep moving, the gas itself as a whole stays in one place, which makes sense intuitively. So yeah, now you know which probability density to use where. If you're assigning component-wise velocity, you tell the computer that pick velocities from this density for 1,000 times for the x direction, and then you pick the velocities again from this density for the y direction and again for the z direction. That's how you can assign velocities to all 1,000 particles. So after assigning component-wise velocities to all particles, say you decide to plot a distribution of their speeds. Then this is exactly what you would get, the Maxwell-Boltzmann distribution for speeds of the particles. Quite interesting, right? So if you're curious on how we relate this expression for the velocity in one direction to the expression for the speed distribution, then you can check out the link I've put in the description. It's from a site Hyperphysics and it has derived this relation. So just to summarize that derivation, it's basically like uh, you you pick a velocity in the x direction from this distribution, and you do the same for x and y, and then you multiply them because they're independent, and that would result in getting a vector like this with magnitude v. I mean, assuming this relation is true, obviously. And but for this probability density for the speed v, this is just one of the possible vectors, right? Um, the total possible vectors that you could have is all the vectors lying on this sphere of radius v, and hence what I've done is multiply this probability density with 1 by 4 pi v square, which is the surface area of the sphere, which results in one of the vectors on the sphere. And so yeah, that's like the intuitive explanation behind this derivation. And if you expand this using the density for velocity in one direction, then you would get this. And since vx square plus vy square plus vz square is v square, you would get the expression for the distribution for the speeds. And yeah, that's the intuition behind it. And if you didn't understand this, you can check out the hyperphysics page because they have explained it in a lot of detail. So I hope you have a clarity on Maxwell-Boltzmann distributions now, and I hope your curiosity is satisfied. So yeah, keep enjoying physics, and goodbye for now.